When a carbon atom collides with a halogen, they lock into a specific geometric relationship. The physical forces binding them in this moment dictate the behavior of thousands of different compounds. This exact carbon-halogen architecture repeats across a massive array of organic molecules, from consumer refrigerants to complex pharmaceuticals. Organic chemistry operates through the same strict physical laws that govern any other mechanical system. Analysis of three specific properties of this bond, its length, its required dissociation energy, and its orbital hybridization, provides a map of how a molecule will behave physically and chemically. We can apply this analysis to two major classes of molecules: aliphatic haloalkanes, which form straight or branched chains, and aromatic haloarenes, built on closed benzene rings. Whether a compound forms a volatile gas or a dense solid, or whether it yields to a chemical attack or repels it, is determined entirely by its subatomic geometry. This diagram compares the four primary halogens: fluorine, chlorine, bromine, and iodine. Fluorine is compact, iodine is massive. As the atomic radius increases, the bond length stretches. A longer bond is weaker. Thus, bond dissociation energy decreases, moving from fluorine down to iodine. Atomic mass directly controls external physical states. The heavier the attached halogen, the stronger the intermolecular forces, which requires higher temperatures to boil the substance. But mass is only part of the equation. This comparison shows a long-chain haloalkane next to a highly branched isomer with the same chemical formula. The branched structure physically reduces the molecule's overall surface area. With less surface area, the van der Waals forces between the molecules weaken. Consequently, branched isomers have noticeably lower boiling points than their straight-chain counterparts. 3D shape directly alters macrophysical states. We see a related geometric effect in the melting points of dihalobenzenes. Molecules with halogens positioned exactly opposite each other on the ring, para-isomers, melt at higher temperatures than their ortho and meta variations. The reason is strict crystalline symmetry. The linear, balanced structure of a para-isomer allows the molecules to pack tightly into a rigid crystal lattice, requiring more thermal energy to break apart. A compound's physical state, as a gas, liquid, or solid, is a direct calculation of its atomic mass, its exposed surface area, and its crystalline symmetry. This split screen compares the baseline structure of our two main classes. On the left, the haloalkane features an sp3 hybridized carbon, bound by a standard single signal bond. On the right, the haloarene is built on an sp2 hybridized carbon within a benzene ring. The sp3 carbon's single bonds are highly polarized, creating a positive charge targeted for chemical substitution. The haloarene has a built-in defense. The halogen's lone electron pairs delocalize, flowing directly into the continuous pi electron system of the benzene ring. This sharing of electrons across the structure is resonance. Resonance changes the physical nature of the CX bond. Because of this resonance, the carbon-halogen connection develops partial double bond character. The bond visibly shortens and thickens, making it more rigid and chemically robust. This reinforced bond physically locks the halogen in place. Nucleophiles, molecules seeking to attack a positive charge and replace the halogen, cannot easily break this shortened bond. The sp2 hybridization and resulting resonance act as molecular armor. This orbital arrangement effectively armors the molecule, preventing the bond breaks that aliphatic chains easily undergo. When aliphatic chains undergo substitution, they are attacked by a nucleophile, an electron-rich molecule seeking to bond with the positively charged carbon and replace the halogen. These space-filling models illustrate how a nucleophile's success depends on steric hindrance, the physical crowding around the target carbon. Moving from left to right, notice the dense wall of bulky methyl groups crowding the tertiary carbon. The primary carbon on the left lacks this crowding. This allows the nucleophile to execute a direct backside attack. In a single bimolecular step known as the SN2 pathway, the nucleophile strikes the back of the carbon, instantly popping the halogen off the front. Because it attaches from the opposite side, this strike causes an inversion of configuration, flipping the geometry like a wind-blown umbrella. But on the tertiary carbon, the nucleophile attempts the same backside attack and bounces off the dense wall of methyl groups. The path is geometrically blocked. This blockade forces the tertiary molecule down a different route, the SN1 pathway, which requires two distinct steps. First, the halogen must detach entirely on its own. This leaves behind an exposed, flat carbocation intermediate. Only then can the nucleophile attack. Because the intermediate is planar, the nucleophile can bond from either side, resulting in a mixed geometric product called a racemate. Molecules do not choose between the SN1 and SN2 pathways. The reaction mechanism is strictly dictated by the physical bulk of the surrounding atoms. Nucleophiles are not the only threat to these molecules. If exposed to an alcoholic base, the reagent doesn't substitute itself into the structure. It strips atoms away in a process called beta elimination. The base removes a hydrogen atom from a neighboring, or beta, carbon. This forces the halogen to detach, and the carbon atoms form a double bond to satisfy their electron requirements. This creates a problem with multiple beta carbons. Which hydrogen does the base steal? Following Zaitsev's rule, the reaction targets the carbon with fewer hydrogens. This geometric preference yields the most highly substituted and therefore stable carbon-carbon double bond. We see a similar thermodynamic preference in haloarenes. While their partial double bonds repel nucleophiles, the dense electron-rich pi cloud above and below the benzene ring makes them attractive to positive electrophiles. When an electrophile attacks, the halogen already on the ring acts as a traffic director. Its resonance pushes electron density toward the ortho and para positions on the ring, steering the incoming group exactly where to attach. Whether an aliphatic chain forms a double bond via elimination, or a benzene ring accepts a new group at a specific coordinate, the chemical outcome follows the path of least electrostatic resistance. When we multiply these physical properties by attaching several halogens to a single carbon framework, we create polyhalogen compounds. The consequences of their subatomic geometry impact human history and the global environment. Look at this early polyhalogen, chloroform. The heavy chlorine atoms gave it specific anesthetic properties used in early medicine. However, it reacts with oxygen, slowly degrading into highly toxic phosgene gas, making it dangerous to store. Compare that instability to the strength of the carbon-fluorine bond. By combining chlorine and fluorine on carbon centers, chemists engineered chlorofluorocarbons, or freons. Their stable geometry made them ideal, non-toxic propellants for aerosols and refrigerants, resulting in their mass production and daily use. These satellite readings show a massive, expanding void in the total ozone over Antarctica between 1985 and 1988. Because the carbon-fluorine bond is virtually indestructible in the lower atmosphere, freon molecules survived long enough to reach the stratosphere, where solar radiation broke them apart and allowed the halogens to shred the ozone layer. A similar persistence applies to DDT, a heavily substituted polyhalogen insecticide. Its molecular structure makes it hydrophobic and resistant to metabolism. Instead of breaking down, it bioaccumulated in fat tissues, resulting in severe ecological damage. The same atomic properties that make carbon-halogen bonds useful in industry, extreme stability and specific reactivity, are what turned them into persistent environmental threats when released at scale. This matrix summarizes our model. A primary sp3 carbon dictates an SN2 substitution. A crowded tertiary sp3 carbon forces an SN1 reaction, and an aryl sp2 carbon demands electrophilic substitution. Organic chemistry is the inevitable expression of bond energy, atomic size, and orbital geometry. Once you understand the physical bedrock of the molecule, its behavior, whether in a test tube, a crystal lattice, or the upper atmosphere, is a logical certainty.